Hello and welcome to part 2 of biotechnology in microbiology. So for this particular short lecture, we're going to look at gel electrophoresis. This tool is a tool that's used quite a bit. It is used to separate fragments of DNA according to their size and their charge. Now in the last lecture we talked about restriction enzymes, and if I expose a plasmid here to a restriction enzyme where this plasmid might have two different places that restriction enzyme cuts, or let's say 3 places just to make it interesting. If it has 3 different places that it cuts, that's going to result in 3 fragments. And these 3 fragments might be of varying lengths. They're going to be of different lengths or size. And length is determined by the number of base pairs. So I want to be able to separate. Now I've exposed this plasmid to the restriction enzyme in a small tube with liquid in a buffer. And the problem I have is I can't see these fragments and I want to be able to see them. So I take my sample and I load it in a gel. And over here on the left we have an example, a drawing of gels. And on the right is what an actual agarose gel or electrophoresis gel would look like under UV light with a dye. So on the left, I have my gel and I take my sample. So in step 1, I've exposed my DNA plasmid to restriction enzymes. I've allowed the restriction enzymes time to do their thing to all of the millions of plasmids that I have in this little tiny tube. I'm going to take some of that sample that has been cut with a restriction enzyme. I'm going to load it in some wells that have been molded into the agarose gel. Now, agarose works a lot like a forest, and a common analogy used is if a rabbit and an elephant ran through the forest, who would run faster? Well, the rabbit would run faster because the rabbit is smaller. So in DNA electrophoresis, in gel electrophoresis, our small DNA fragments are going to move through our gel very quickly, and the larger fragments are going to move very slowly. And this is going to allow me to separate these DNA fragments so I can see them at different regions within the gel. How do I separate them? I apply electricity. So I have a electrophoresis chamber. Inside of that chamber is a small platform that the gel will rest on, and the gel will be immersed in a liquid buffer. On either side of this tray here is going to be an anode and a cathode. The anode is the positive end, that's what you see down here, and the cathode is the negative end up here. And DNA as a molecule, its sugar phosphate backbone, lends DNA a very negative charge. So the DNA molecule has a negative charge. I load it in the negative end of the electrophoresis chamber, and when I apply an electrical current to run through my buffer, which in turn will cause it to run through my gel, my negatively charged DNA will be attracted to the positive end. But since it's trapped in these wells inside of the gel, it has to move through the gel to get to that positive charge. That gel is the forest. And so as these molecules run through that agarose gel, the smaller ones move very quickly, the larger ones move much more slowly, and what I end up with is over here on the right, I end up with separated fragments. So where I see these bands on my gel, I have a collection of DNA fragments that are of the same length. So if I cut this into 3 fragments here, I would look for a lane that would have 1, 2, and then maybe a 3rd fragment down here. And this would be the plasmid that I cut that I'm looking for. On the right, we usually run a DNA marker. These are, this is a set of standards, and these are fragments of known base pair lengths. I know exactly how many base pairs are in each of these fragments, so that if this one here, this fragment here, contained 1,200 base pairs, I would know that this fragment from my plasmid also contains 1,200 base pairs because they ran the same distance at the same time in the same electrical current on the gel. So electrophoresis, gel electrophoresis is used for a lot of different things. I can use it to compare DNA samples from multiple organisms. I can use it to carry out a process known as DNA fingerprinting, which is what's used in forensics when they're comparing DNA from a crime scene to a victim to suspects. I can use it to sequence DNA. We're going to look at that in a lecture. I can use it to identify a microorganism, which is similar to forensics, but in this case in microbiology. I can also use it to make sure that a PCR product is there. I can use it to chop up DNA into 1,000,000 pieces and then add a probe and find a specific piece of DNA. We're going to see gel electrophoresis pop up in a few more lectures. So here are some examples of some DNA gels. At the bottom left, this is kind of your typical crime scene one. So this is this is called a DNA fingerprint. Both of these are actually DNA fingerprints. Here we have the victim. So the victim's DNA was cut. My pen is not working again. My victim's DNA was cut with a set of restriction enzymes. The specimen that was found at the crime scene was cut with the same set of restriction enzymes. And this is done, the victim is there as a control to make sure that the DNA found at the crime scene that they're testing is not the victim's. So you can see where all these bands are. The victim does not contain this band here. The victim does not contain these bands here. And there's a lot of differences between the specimen at the crime scene and the actual victim's DNA. So we now know that it's not the victim's. Then we have our 3 suspects, and you can tell that it's not suspect 2 because suspect 2 has bands here, but the specimen does not. We know it's not suspect 3 because the specimen has this band here at the top, and suspect 3 does not have that band. But so far, it looks like suspect 1 matches. And you can see we look all the way through where all of these different bands occur, it's identical. So here we have an obvious match between suspect 1 and the specimen found at the crime scene. Here at the top left, we have a similar type of situation, and this is in microbiology. So in the top left here, we're looking at an electrophoresis gel, and there was an outbreak of an E. coli infection in a hospital, and they used this electrophoresis gel to determine where that E. coli infection was coming from. They realized it was coming from apple juice, and then they went through patients who had had apple juice, and they took E. coli from those patients that were showing the signs and symptoms of that infection, and they ran a DNA fingerprint between the isolates from patients who drank juice, isolates from patients who did not drink juice, and compared them to isolates from the actual juice itself to see which patients got their E. coli infection from the apple juice and which ones did not. So last, I'm going to show you a quick video that kind of shows you how DNA gel electrophoresis works.
Once DNA has been extracted from a sample and a section bearing useful code such as a VNTR or STR is isolated, the next step in DNA fingerprinting is to measure each strand and count the number of repeated sections. To do this, scientists use a technique called gel electrophoresis, which uses an electric current to push strands of DNA through a slab of gel-like material. Because each bit of DNA is negatively charged and subject to an equal electric force propelling it to the positively charged side of the gel, smaller pieces move faster than larger ones. When the current is removed, the gel is photographed to reveal how far each bit has migrated. By comparing the bands produced by the DNA samples of interest with bands produced by standard samples whose sizes are already known, the precise length of each DNA fragment can be gauged.
So that's just a quick video that also reviews how DNA gel electrophoresis works. So this is it on gel electrophoresis. I will see you in our next one in biotechnology.